Hello, everyone. In this topic, I wanted to talk about a little bit of notation, really. A short way of writing down what we mean when we talk about expectation values and probability and finding things out about the wave function. So we're going to borrow a little bit of ideas from statistics because ultimately what we're talking about with the wave function is we want to interpret the sort of magnitude squared of it as a probability. And so we're going to want to figure out things like, okay, the particle. So we're thinking of an electron as a wave, but like, okay, where is it? It's a wave. It's spread out, but on average, it has some average position. So we want to figure out like, how do we talk about that? How do we find it? How do we compute it? How do we write that down? So I just wanted to go over that today. So if you remember, we have this wave function, and for now, we're just going to worry about the space part, because that's what we're going to be worrying about most of the time. And we said that we interpret this as basically related to probability, but to actually get back to probability, we need to multiply it. We need to take the absolute value squared, which is the same thing as multiplying it by its complex conjugate. And so this thing is what we interpret as basically a probability function, saying what the probability of finding that electron or whatever it is at any given position. And what we want to make sure about our wave functions when we solve for what they are is we want to make sure that when we integrate over all possible places, that we get 1. We get 100%. We have a 100% chance of finding that particle somewhere. If we go over infinity, we're going to find that particle. But that's going to basically set an overall constant when we solve for our wave functions. But I don't want to talk about that too much right now. What I want to talk about is that we're going to be doing sort of integrals like this a lot. And in fact, what do we say? How do we say what is the average position of that particle? If it's a wave, but what is its average position? And so we could look at this though, and we could say, well, that's the probability. Then how do we take a probability and find sort of an average from it? So for example, it's a lot easier to think about if you think about this is a continuous probability function, but you can also think about discrete probability functions like rolling a dice. Dice, that's plural, but whatever. Rolling a die, a 6-sided die, you have a 1 in 6 chance of getting each result. And then you say, well, what is the average result when you roll? Well, you take the result, the number on the die, and multiply by the probability, a sixth, hopefully, if it's fair, and sort of add that all together, and you should get like the average roll. And so that's actually pretty much the same thing that we're going to do with this probability function. Only instead, because it's continuous instead of discrete, we multiply this p of x by the thing that we're actually trying to measure. And instead of adding up all the results, doing an addition, we do basically an infinite sum, which is an integral. So that's how we're going to deal with this. We're going to say, and so what we say is if we want to find the average value of x, we take x, multiply it by the probability for x, and then just integrate that over all the possibilities. And so that's what we call the average value of x, or in this context, sometimes we call it the expectation value of x. And we have a way of writing it, which was with these kind of angle brackets, which are usually a little bit steeper and taller than less than and greater than signs, but it sort of looks like this. So you'll see that. What that really means is that's an average, or another way of saying it is expectation value of x. What that means for the case of quantum mechanics, I mean, this is in general statement about probabilities, but what this means for quantum mechanics is, of course, if that p of x is just the wave function times its complex conjugate, that means then if we have a wave function, we can find the average value of it. Do I have room for a dx there? Yes, I do, just barely, by doing that integral. But it's a lot nicer to have this sort of shorthand way of expressing that, because this is something we're going to want to do a fair bit, but it's kind of nice, at some point we do have to do an integral, but it's nice to have a shorthand way of writing it. So when we write this sort of angle brackets surrounding an x, we mean the average or expectation value of x, and that's how we write it out as an integral. And so I wanted to introduce that notation and also go through a couple of examples and sort of some of the properties of that to get a little bit used to working with it, because that's what we're going to do a fair bit. And then we'll see it more later on. But for example, since we're just multiplying that by the function, if we have, let me write it down this way. If we want to take the expectation value of something else, we can usually break it up into pieces. So let me actually first write this. Let's say we want the expectation value of x squared. That just means the integral minus infinity to infinity of x squared times psi of x times psi star of x dx. One note I would actually say is that for many of the problems we'll consider, this wave function, just the space part of the wave function, will be entirely real. So the complex conjugate is just the function itself. That'll be often the case, but not always. So we should be a little bit wary of that. So often you'll just be basically squaring the wave function, but just keep that in mind, that it's really a complex conjugate. That's the expectation value for x squared. And so what we often want to find, though, is we say, okay, this first thing I've computed, this is the average value of x. But often, like we said, it's a wave. It's spread out. It's not always at the average. It's not really a particle that's just always right at its average point. It's not a point particle. It's a wave. It's spread out. So we often want to know not just what its average value is, but what is its, you can call it uncertainty, but really what is its spread? It's spread out over some range. And so we're looking at basically sigma x, just like we would do if we were looking at a purely statistical uncertainty. But I want to emphasize in this case, it's more of a factor that this is a wave, and we're looking at something that is just fundamentally spread out. But we can use the same math basically, and so we can say, well, this is its average position, but what is its standard deviation? And the standard deviation is basically the way I would write it in this notation is it's the average value of its position minus the mean position. Sorry, didn't leave myself enough space. So I would write it as the square root of the average value of this minus this squared. So it looks a little complicated, but the nice thing is that this simplifies, and so that's what I wanted to work through in this notation, because we can basically, this looks like, oh my god, I have to do an integral inside another integral and all this stuff. But actually, no, we don't. We can work through sort of some of the behavior of this without actually having to do any integrals and get some interesting results, because we know ultimately that it does relate to an integral, but we know how that behaves. So let me first do one thing here. Let's write out, we've got this squared here. This is a standard deviation. Let's multiply out the square. Angle bracket, let's see, x squared minus, I'm going to have cross term. It doesn't really matter which order they go, so I get 2x times the expectation value of x. And then I have plus the expectation value of x, that quantity squared. And then I need to take the expectation value of this whole thing. Then I have this square root at the very end. All right. So we have that. Still looks a little rough, but we can use some properties of integrals to simplify this out. So let me clear some space up here. Leave that down there. Because let's look at this thing inside the angle brackets. If I have the expectation value, let's just actually kind of think generally about how these expectation values work. If I have an expectation value of some function of x plus some other function of x, that basically, what does that mean? That means an integral of f times psi. Well, it means an integral of f plus g times psi star. But I can multiply this out. So I can write this as the integral of f times psi star. This is looking like a horrible mess because all my lines are blurring together. But I think you hopefully see what I mean here. I can basically just multiply this out, and I can say, oh, this is the same thing as the expectation value of f plus the expectation value of g. You probably could have guessed that, but by writing out the definition there, we can be very clear and explicit about it. Basically, the property that this has mathematically is just this sort of operation of taking the expectation value. It's linear. If we add two functions together, it's the same thing as doing the thing and then adding. And if we multiply by a constant, we can factor that constant out, and so on. So we can use that. So let me actually clear that out, because that means this big thing in the angle brackets can be written. I'll keep that square root there. The angle bracket, we can just break out all the terms. We've got the expectation value of x squared. We've got, I can factor out the minus 2. We've got the expectation value of x times the expectation value of x. We'll have to come back to that. We'll think about what that means. Plus the expectation value of an expectation value squared. All right, let's talk about that last one, actually. An expectation value is an integral over the variable. And so when we're all done with that, it's basically just a constant. When we integrate some function of x times the wave function times its complex conjugate and integrate over x, what we get at the end is just a number. It doesn't depend on x because we integrated over that variable. So this inner expectation value of x, that's just a constant. So if we take the expectation value of just a constant, of just a number, and then take the expectation value of that, well, the average value of a number is just the number itself. So it's, for example, if you want me to write it out, like if I had 3 times the wave function times its complex conjugate, and I integrated over all x, I can just pull the 3 out, and then I just have integral of psi times psi star over dx. But this, we said, if we want probability to work out the way we expect, that should be just 1. So the expectation value of a constant is just that same constant. So using that, once we take the expectation value, we get a constant. And so if we take the expectation value again, it doesn't do anything. We just get the same constant back. So this third term is just this. It's just the mean, the square of the mean of the average value of x. Taking the expectation value again doesn't do anything. Now, having said that and maybe written it out, we can kind of think about what happens with this middle term. Here we're taking the expectation value of x times, let's forget about what this is, but it's just a constant. What that means is we can take this constant here and this inner one, and we can kind of pull it out of the integral, because each of these angle brackets implies an integral. What this means is we can actually write this middle one as minus 2. We can pull this inner one sort of out of the integral, write that as like that, and then what's left inside is just that same thing. So we can write it that way. And then the first term we just leave alone. We can't really make that any easier. And we have square root of the whole thing. Okay, so now you'll note, hey, wait a minute. This middle term and the last term are actually really the same thing. I've got the expectation value of x times itself. That's really just the square, and this is the square of that. So this actually then just becomes square root this, and then I have minus 2 of these plus 1 of those, so I'm left with minus 1. And so this thing in blue is just another way of writing the standard deviation. That's a little bit easier to compute than this one in black. because then here I really only have to do two integrals, and they're each fairly straightforward, and then I'm done. I do want to point out that these two terms, they look kind of alike, but they're different things. Remember, because this is sort of the average value of x then squared. This is the average value of x squared, where you take the square first and then average. And so those are different things in general. If you have any kind of spread out quantity. So I'm going to wrap up there. But that's kind of the notation of sort of expectation values. Later on, we'll talk about not just position, but we'll also want to talk about momentum, but I'll leave that for another topic. But this is skipping ahead a little bit, but this is a nice little bit of notation that you'll see again, and it's kind of handy to write this out, and we will be making use of. We will want to know where particles are. We will want to know, like, what's the position, what's sort of its average spread. And in fact, we can relate this standard deviation, that's basically the delta x that when we talked about in uncertainty relation. So we're going to be able to relate that all back to what we know about things behaving as waves.